Hello, and welcome to Western Civ, episode 270, Galileo, Part 2. Last week I introduced Galileo, discussed his early life, and more or less worked up to the point that he was a relatively unknown professor at the University of Padua, focusing a lot on the differences between Aristotelian logic and the new type of logic that Galileo was endeavoring to imprint on Europe. Kind of like fighting an uphill battle, unfortunately. And for frankly, hundreds of people in the early modern period, that's precisely where the story ends. An unknown professor in some university. But not Galileo. As we've already seen, there's something different in men like Copernicus, Tycho Brahe, and now Galileo. For thousands of years, Europe had been ruled intellectually by classical and ancient philosophers. Men like Plato and Aristotle, men who would have been more at home in the world of Socrates and Alexander the Great than Christopher Columbus. But the world was changing. Galileo recognized that. That is what makes him unique, or if not unique, at least part of a new breed of European, of a new breed of human. People today we call scientists. Certainly, if we think about Galileo the scientist, the years 1592 to 1610, when he was teaching at Padua, were undoubtedly the most important of his life. During this period, he made all his major discoveries. The bulk of the findings that he put into his two largest works, the Two Sciences and Dialogue, two of his most consequential works, they all come from this period of his life. Yet our actual record for him during these years is shockingly thin. That's very unfortunate for us. The reason being is, of course, that during these 2 decades, Galileo also critically converted to Copernicanism. Now, Copernicus published On the Revolutions of the Heavenly Spheres in 1543, and he died that same year, as we know. In his seminal work, Copernicus argued that the only way the evidence of astronomy made any sense was if humankind accepted the proposition that the Earth was a planet, just like the others, and that it, like Mars and Venus, orbited around the sun. Now, Copernicus's universe did have a center. Technically, it's like really near the sun, but not quite the sun. Now, astronomers, even astronomers of this age, they're perfectly happy to think about a universe that included a moving Earth. After all, as Copernicus pointed out time and time again, this was the only way that the night sky made any sense. But philosophers are a different story. And remember, in this era, philosophers are considered much more important, much more prestigious than scientists. Philosophers, still desperately clinging to Aristotle, refuse to accept these conclusions. Again, we must remember that science, as we know science today, was not the science of the early modern period. First and foremost, philosophy and its emphasis on deductive reasoning was the most important branch of science by about 1,000,000 miles. Everything else was of lesser value. Physics, back then, was merely a branch of philosophy. So long as university philosophers remained opposed to Copernicanism, it was dead on arrival. Frankly, in the decades after his death, there were no full-fledged followers of Copernicus. Astronomers liked his work, but they liked it primarily because of the accurate charts that were in it that simplified calculations. Nobody was ready to die for Copernicanism or his ideas, at least not yet. Now, a crucial reason for the lack of support for Copernicanism lies in the existence of a new alternative to geocentric system of Ptolemy and the heliocentric system of Copernicus. And this was, of course, the geo-heliocentric system of Tycho Brahe, first described in print in 1587. According to Tycho, the Earth was, as Ptolemy and the Aristotelians claimed, stationary at the center of the universe, and the sun, moon, and fixed stars revolved around the Earth. But the planets, Tycho argued, following Copernicus, revolved around the sun. These three systems were so fundamentally different that you might at first think it would be easy to find evidence to settle the question of which one was right. But if one allows for adjustments of scale, and scale is of course massive when we're talking about the distance between the planets, they're each capable of making pretty good predictions for the positions of the moon, the sun, and planets in the sky, which were identical to those made by others. In fact, they're really almost geometrically equivalent. It was soon apparent that naked eye astronomy was just incapable of choosing between them. So really then, the fundamental choice isn't which one's possible. It's which one is plausible. Which seemed more likely, that the Earth rotated once a day, or that all the fixed stars rotated around the Earth once a day? Which was more plausible, that the Earth was just another planet, or that the vast bulk of the sun circled the Earth every day, carrying all the planets with it? When thinking about questions like these, objections to a moving Earth, which were really physical, honestly, rather than astronomical objections, all these questions become central. Now, matters started to change in 1609, and that's because of new evidence, not new theories. And I'm talking about new evidence from telescopic observations, above all made from the observations of Galileo. And of course, in the same year, Johannes Kepler also published New Astronomy, in which he argued that no theory which insisted on circular movement could account for the orbit of Mars, which he was, claiming at least, was an eclipse. Galileo was at the forefront of telescopic revolutions. He simply avoided discussing Kepler's revolutionary proposals. Frankly, he probably doubted whether Kepler's measurements were sufficiently reliable. He surely found his arguments implausible, and he probably felt that they offered the opponents of Copernicanism new grounds for rejecting the Copernican system. Galileo remained, honestly, to the end of his life, an old-fashioned Copernican. It seems very likely that when Galileo became a Copernican, he had never once in his life met a follower of Copernicus. There just weren't really hardly any of those. One of the greatest Copernicans alive in 1592, and certainly of those who had already published in support of Copernicanism, was a man named Giordano Bruno. Bruno was a philosopher rather than an astronomer. He wasn't just a Copernican. He also believed that the universe was infinite, that there were other inhabitants circling other suns. No, not surprisingly, he was never able to secure employment as a philosopher at any university, as all of these ideas flew in the face of everything that had been taught for roughly the last 2,000 years. Bruno, we know, was in Venice when Galileo arrived there in early September to lobby successfully for an appointment at the University of Padua, an appointment that, ironically, Bruno had hoped to win for himself. But by September, Bruno was already in prison. He had been imprisoned by the Venetian Inquisition. He had been there since May and was be transferred to Rome in February of 1593. Venice exercised firm control over the Inquisition within Venetian territory, as an aside. It seems certain that Venice would never have permitted Bruno to be handed over to Rome had he been a Venetian or a teacher or even a student in Padua. But he was just a visitor, and the Venetian state had no interest in protecting him. Once in Rome, Bruno was repeatedly tortured and eventually executed, burnt alive in the year 1600. Now, it's inconceivable that Galileo did not hear about Bruno during these early years. He worked in a library which contained copies of Bruno's works. Again and again, his views were compared to those of Bruno. Yet in all of Galileo's surviving works, his books, his letters, his notes, his drafts, there's not a single reference to Bruno. Curiously, the exact charges against Bruno were and remain unknown to posterity. The record of his trial was destroyed in the 19th century. We know, however, that Galileo was influenced by Bruno for one key reason: his rhetorical style. In Plato's writings, for example, Socrates, the philosopher who's always right in any of Plato's dialogues, always speaks for himself. He's the voice of reason. Or I should say, I suppose, or rather, Plato speaks through him, but he's his mouthpiece. But Socrates has a name in these dialogues. For Bruno and subsequently Galileo, the speaker who is always right, man who's always in the right, is an unnamed philosopher. Bruno was really the first one to do this, and the fact that Galileo parroted him so clearly gives an indication that Galileo must have known about the man. Now, Galileo's first documented contact with a committed Copernican came in August of 1597. He wrote a letter to Kepler, who had published the first major development within Copernican astronomical theory, a book titled The Cosmographic Mystery, back in 1595. This argued that the proportions of the solar system were determined by the shapes of the 5 regular solids: the pyramid, the cube, the octahedron, the dodahedron, and the isohedron, figures with 4, 6, 8, 12, and 20 sides, respectively. This was all first described by Plato, by the way. Kepler had given 2 copies of a book to a friend who was traveling in Italy, and he ended up giving them to Galileo. Kepler was probably astonished to receive a letter out of the blue in which Galileo, a man quite unknown to him, declared that he had been a Copernican for a number of years. This letter is probably, and it really is in just about every history I've read of Galileo, the most important single document for understanding Galileo's intellectual biography. It obliges us to adopt a very different view of Galileo's intellectual trajectory, to which had genuinely be accepted. Now, getting back to Galileo and Copernicus for a moment. As a mathematician, Galileo would have been required to teach different astronomical systems. And hence, he simply must have known about Copernicus. In Galileo's book, On Motion, he references a technical detail described in Copernicus's work. So we know that by 1592, Galileo must have read Copernicus. Again, it is unfortunate that we do not have any direct written evidence to confirm these dates, but we don't. So we will just have to put together what we can. What I can say definitively is this: Galileo was not a Copernican when he left Pisa in 1592, but he became one shortly thereafter. When Galileo wrote to Kepler in 1597, he made a remarkable claim. He said not only had he been a Copernican for a long time, but he claimed that, quote, "With this hypothesis, I have been able to explain many natural phenomena, which under the current hypothesis remain unexplainable, end quote. He had, he said, written at length in defense of Copernicanism, but had no intention of publishing while Copernicanism remained so genuinely and generally scorned. Galileo, it's worth noting, was employed, like the rest of the professors, through a series of renewable short-term contracts. So he could not afford to adopt in public views which were so genuinely disregarded. But by 1597, he appears to have already been working on an early version of what would eventually become his masterpiece, the, quote, dialogue concerning the two chief world systems, end quote. This is the problem, though. The defense of Copernicanism that Galileo wrote sometime between 1592 and 1597 has not survived. Now, there is good tangential evidence regarding Galileo's thinking when he first arrived in Venice. In 1592, his friend and sponsor, Galileo del Monte, invited Galileo to visit him, and we can surely date that visit to the summer of 1592. And Galileo conducted an experiment at that time. We have Del Monte's notes, and he and Galileo probably did it together, the idea for which may have indeed been Galileo's. The experiment was a very simple one. Take a hard ball and coat it with a substance that would leave a mark. Take a hard, flat surface and place it at an angle fairly close to the vertical. Then, throw the ball so that, like a pinball, it flies across the sloping surface, first rising and then, after it slows, falling. What will be left behind is the track of the ball across the surface. And this track should be very similar to the path of a ball flying free through the air. In other words, the path of a projectile. The experiment showed two things. First, the path of the ball is symmetrical curve. The projectile never travels in a straight line, and its path while rising is identical to its path while falling. Second, the curve is mathematically legible. Galileo and Del Monte felt it was very similar to a parabola. The result, however, was an astonishing rejection of Aristotelian physics. According to Aristotelian physics, an object's movement was governed either by nature or by force, not both simultaneously. Hence, a cannonball shot out of a cannon should proceed straight until it runs out of force, and then it should fall straight down at a right angle, which is when nature takes over. But of course, cannonballs don't fly like that. Now, as an aside, by the way, you might be sitting there thinking, hey, a child throwing a rock could have been immediately able to correct Aristotle, but I guess that didn't happen. Galileo was, in 1604, still trying to make sense of all this. Obviously, what Aristotle claimed was not how projectiles appeared to move, so what was the problem? Galileo realized in the end, Aristotle could not be correct. In On Motion, he theorized that acceleration was temporary, and that projectiles were impacted by a constant rate of fall, which is true. He could never quite prove it, but that did remain the theory throughout his life. When Galileo wrote On Motion, he was not a Copernican. He did not even address the question of falling bodies on a moving Earth, because even though he had formulated the idea of circular inertia, he assumed that Earth was stationary. It looks very much as though by the time he left Del Monte's, he had become a convert. In fact, it's even possible that Galileo had converted Del Monte, as he left in his papers when he died in 1607, a treatise on the movement of the Earth. What had converted Galileo to Copernicanism was not some new understanding of astronomy. It was a new approach to the problems of physics he had been addressing in On Motion. Galileo became a Copernican because he now had the conceptual apparatus with which to understand the physics of a moving Earth. But his conversion implies an eagerness to embrace Copernicanism, for he had found no new evidence in favor of it. He had merely found a way of refuting one of the standard objections to it. Conversion for Galileo was remarkably easy. He was a mathematician and so could appreciate the beauties of the Copernican system. He was hostile to Aristotelian philosophy and so had no attachment to the old order. Based on some of his other writings, he believed neither in heaven nor in hell, so he had no need to worry about where these two locations were spatially. He will have been well aware that the arguments that convinced him would not have been enough to convince other, more conventional thinkers, though. Still, by the time Galileo arrived in Venice in 1592, he had formulated sophisticated responses to the standard arguments against a moving Earth, arguments that went far beyond anything in Copernicus. He could explain why objects dropped from a high tower appear to fall vertically by means of principles of circular inertia and combined movements. And he could explain why objects are not thrown off into space by centrifugal force by comparing the estimates of speed at which bodies fall towards the Earth with estimates of speed at which they would move away from the Earth if projected along a tangent. This being established, it's possible to revisit Galileo's remarkable claim in his letter to Kepler that he had used Copernicanism to explain many natural phenomena which were inexplicable within conventional physics. Kepler immediately guessed that Galileo was talking about the tides. The tides, believe it or not, are actually going to be one of sort of this continuous problems that Galileo comes back to throughout his life. This seems to have been an extraordinary leap until we realize that a classical source had suggested that the tides might be linked to the movement of the Earth. And Kepler, by the way, was right. For in notes from 1595, we find an account of the theory that Galileo was to put forward in 1616 and published in 1632 as proof that the Earth moves. The basis of the argument was shockingly simple. If you're on a boat, which a little water has leaked into, the boat and the water within it travel along quite happily. But if the boat bumps into a bank, the water in the bottom of the boat carries on traveling forward, piling up in the front of the boat. The tides, Galileo argued, must be caused by a similar phenomenon, by some change in speed or the direction of the Earth's movement, which causes the water contained in the Earth's basins to slosh around like it does in the bottom of a ship. Copernicus attributed 3 movements to the Earth, of which 2 were the most important. One was the annual movement around the Sun and the daily rotation around the axis. The combination of these movements would, Galileo argued, mean that any point on the Earth's surface would be traveling faster when it was on the side of the Earth away from the Sun. In between would experience acceleration or deceleration. Of course, this is not in fact what causes the tides. They are caused, as Newton will show, by the gravitational attraction of the Moon and the Sun. But it could cause tides in a theoretically possible world. The argument is valid in principle, but not in its application to our particular planet. That it is the wrong explanation for tides in our world was never apparent to Galileo, who refined it to explain why tides vary at different times of the month and year, and who sought to explain away the fundamental problem that there are 2 tides every day rather than 1. His theory would have implied 1. Nor did Galileo have an explanation for the fact that the timing of the tides varies from one day to the next. In the new physics of Galileo, rest and constant movement are indistinguishable, and this alone can explain how objects behave in boats. When Galileo says he has used Copernicanism to explain many natural phenomena, he means that he has used his new principle of the absolute relativity of movement, a principle which must be true if Copernicanism is to work, to explain a wide variety of phenomena. Now, there's another discovery that Galileo probably had in mind when he used the word many in his letters to Kepler. In his first great work, The Starry Messenger, he talks about a discovery, quote, not made recently, but rather many years ago, unquote. This discovery related to the faint light illuminating the dark mass of the moon at new moon. Some had claimed that the light came from the moon itself, some that it came from the stars, and some that it was the sun's light shining through the translucent body of the moon. Galileo claimed, correctly by the way, that the light is what we now call earthshine. In other words, that the Earth illuminates the moon just as the moon illuminates the Earth. The argument he presented wasn't new. In fact, you could find it in one of Leonardo da Vinci's notebooks. In The Starry Messenger, a crucial argument for thinking of the Earth and the moon as alike is that the moon is not, as Aristotelian philosophers claimed it was, a perfect crystalline sphere. Now, Galileo said that was nonsense. It has mountains, it has valleys, it's not a flat surface. The mountains can be identified by the shadows they cast, and by the fact that their peaks are caught by the rising sun, lighting effects that are clearly visible with a telescope. In The Starry Messenger, the impression is given that it is a completely new argument. But this was a phenomenon Galileo discovered almost as soon as he turned his telescope to the moon in 1609. Yet, he showed no initial urgency to publish this extraordinary finding. Then there's the next thing that he took at issue with the Aristotelians, which is distance. Remember, Aristotelians claimed that our universe was finite and, frankly, quite small. Taking the measurements of the universe accepted by Aristotelians, Galileo maintained that displacing the Earth from the center to the location of the sun would be equivalent to seeing 176 degrees and 56 minutes of the sphere of the heavens at night and 183 degrees and 4 minutes during the day. A difference equivalent, if the Earth was at the center of the universe, to seeing the heavens from the top of a mountain 1 mile high. It's easy to see, he argues, that this difference might be imperceptible, and we will certainly not be aware that the stars above our head are closer than the ones on the horizon if the scale of the universe is increased, as the Copernican theory required. What Galileo is trying to do here is put together a fundamental but critical claim. If we look at the heavens with the naked eye, either at a single moment in time or over the course of the day, there is nothing that we can see that could help us choose between the Copernican and Ptolemaic systems. Between 1591 and when his father died, and 1610, Galileo was engaged in a constant struggle to try to just make ends meet. It seems likely that his sister married in 1591 on terms negotiated by his father. Galileo, sadly, inherited only the obligation of paying for her dowry. And in 1593, we have evidence that his brother-in-law was threatening to have Galileo arrested if he came to Florence because he hadn't paid. Galileo borrowed 200 ducats to sort things out. In 1601, the marriage contract for his other sister provided for a dowry of 1,800 ducats, once again to be paid over a period of 5 years by none other than Galileo and his brother Michelangelo. But of course, no money was going to be coming from Michelangelo. In fact, Galileo had just spent 60 ducats equipping Michelangelo so that he could take up a job in Poland. In 1602, we find Galileo again borrowing 250 ducats, which he was unable to repay. He had to return to his friends for help after his employers agreed to pay him only a year's wages in advance when he asked for 2. A year later, he obtained a second year's salary in advance. Nevertheless, in March 1605, he was once again being sued twice for both of his sister's dowries. 1608, he was forced once again to ask for his salary in advance. We can see how difficult Galileo's financial position was when we recognize that the younger sister's dowry represented close to 30 years' salary at the rate that he was being paid at Pisa, and 8 years' salary at the rate he was being paid at the University of Padua. At Pisa, he had been paid 60 ducats a year. In Padua, he started at 180 florins, a Venetian florin being worth about 70% of a Florentine ducat. Again, he got a new contract in 1599, and the salary rose to 320, and in 1606, ballooned to 520 florins. His improved telescope led to his being offered a contract for life at 1,000 florins a year, but this didn't start until 1612, well after all of the financial problems. And in fact, in 1612, the university stipulated that there would be no further wage increases. Before 1606, Galileo simply couldn't meet his financial obligations out of his university salary. Moreover, he soon had a mistress, Maria Gamba, about whom little is known and whom Galileo left behind when he moved to Florence in 1610, and children of his own to support. He had 3, a daughter, Virginia, born in 1600, Livia in 1601. By the way, as an aside, I didn't give you their names, but those happen to be the exact same names of his sisters. That's why I didn't give you the names, because it gets confusing. And then he had a son, Vincenzo, in 1606. He was able to supplement his income by teaching, or rather tutoring, mathematical skills required by young gentlemen who wanted to pursue military careers. How much he brought in from this, though, is really difficult to say. Galileo probably, early on at least, earned about 3 times more from private lessons, people that he kept on his borders, and the sale of telescopes and other instruments than he did from lecturing at the universities. So it's fascinating to think that, in these years when Galileo was his most intellectually productive, he was under unbelievable financial stress and burden. The fact that he had the time to sneak away and stare at the night sky to develop the theories that he once would is just fascinating. These were the years in which Galileo was carrying out an active program of experiments. Frankly, long hours of teaching probably seemed like an unbearable distraction. He came to hate teaching so much that he later wrote about it as being equivalent to nothing more than prostitution. It's not surprising that he began to long for a better life and to make inquiries as to whether or not he could find employment elsewhere. What he was looking for was not necessarily more money, but more time. When he finally moved to Florence in 1610, the salary was about 40% more than he was to have received if he remained in Padua, but a good deal less than if he had stayed in Padua and continued providing lessons. The big difference was that in Florence, he wasn't going to be required to do any teaching at all, not even the 60.5 hours a year that were required under his current university contract. This was what he called leisure time, not money or status. That was the irresistible attraction that caused him to leave Padua. And there was another attraction, though. In Padua, Galileo had been dependent on the patronage of a small circle of powerful young noblemen. They had looked after him, ensured his salary was regularly increased, and arranged for it to be paid in advance. And of course, they had lent him money when he needed it. But in return, they expected to be able to make demands on his time and energies. They expected him, for example, to go with them when they went on vacation. The demands of such friends and patrons came to be seen as so burdensome that satisfying them involved what Galileo saw as, quote, ceaseless labors, end quote. It seems clear that he had come to resent this unequal relationship. Luckily for Galileo, after he moved to Florence, he had a good income and he was never in financial difficulty again. When Galileo arrived in Padua initially, there was a major reorientation in his intellectual interests. On Motion was a purely philosophical work. By contrast, his very first surviving letter from Padua is concerned with a practical problem in naval technology, i.e., how long should the oars of a galley be? There could be no more basic question in Mediterranean naval warfare in the period. Fighting was entirely conducted, as it was in the Roman era, by boats powered not by the wind, but by bodies of human beings. This new interest in technology was soon reflected in a number of different areas of activity. Galileo wrote courses of lectures on machinery and on fortification. He designed and sold his sector or compass. He designed a drainage pump of some kind. His primary interest was now in applied science, and this new interest went hand in hand with an interest in developing experimental procedures. The birthplace of modern science wasn't really Galileo's lecture room in Padua, but it was a place that the Venetians called the Arsenal, the vast shipyards where vessels were built and repaired for the Venetian navy. But it still took Galileo a long time to learn this new craft of applied sciences. Time and time again, he got into arguments with individuals in the Venetian Navy about how long the oars should be. His fundamental problem was he never actually went down and talked to an oarsman. He never talked to a shipbuilder. All of his models were purely theoretical, and none of them worked in real life. So again, what we have here are a lot of baby steps. Galileo never fully grasped that theory had its limits and that one needed to learn from experience. Ultimately, what Galileo never came to terms with was that he needed to use experience in order to guide and on occasion even change his theory. Galileo, though he was arguably the world's first experimental scientist, never understood, at least never fully understood, the need to use experience to inform his theory. I don't think we should be too critical of him for this. After all, remember, we're coming out of an intellectual age when all that mattered, and I mean 110%, was theory and deductive reason. For 1,000 years, if the theory said one thing but you experienced another, then your experience was wrong. Galileo was slowly but surely breaking out of that mantra. But it would take time, and I don't want to fault Galileo for his inability to jump forward hundreds of years in just a few decades. Certainly, Galileo taught and studied applied science. That being said, his fundamental approach to the subject was theoretical, not practical. He was interested in clarifying principles, not creating machines that could actually work. In fact, of all the drawings and plans Galileo made, only one, historians agree, could have actually functioned. Galileo was never thinking about real machines. He wanted a way to test theory. But there's no such thing as a pulley without friction or a rope that has unlimited tensile strength. Not that that stopped Galileo from writing about any and all of these things. So while he might be inching towards a new science, his inclination was to use his innovations to power previous thinking. All right, we're going to leave it there for today before we really start to get into some of the heavier astronomy in our next episode. If you're itching for more Western Civ, you can check out either of the 2 7-day free trials in the show notes. You can get links to the Patreon page and to Western Civ 2.0. Western Civ 2.0, we are well into the wars of the successors and beyond at this point. Alexander the Great has been dead for some time, and everyone's still fighting over the carcasses of his empire. It's good stuff and fun, and if you would like to check it out, just click either link or head to the website. Links also in the show notes.